Hey everyone, welcome back. This is episode 5 of Learning Motion Control and I/O with PLCs. I'm using Beckhoff here, and on the last episode, we were talking to some hardware. We did that over EtherCAT, and we're able to read in a prox over a digital 24-volt signal, output to these blinking bits, and it turned on the lights on our pod, which essentially means that we could flip any kind of contactor or relays, things like that. So I didn't really go into much detail about the actual field bus that we're using. So the field bus we've chosen here is Beckhoff's kind of go-to. Their entire PLC system, you can use it without EtherCAT, but I don't know why anybody would really want to. It's very tightly integrated and it just works really well, super flexible. So I'm going to talk about why that is and a few things about it. And then in the next episode, we'll get into bringing in those servo drives and actually getting them spinning and things like that. Let's talk a little bit about the topology of an EtherCAT network. I have this unfortunately low resolution picture here, but over on this left side here we've got our controller. So that's the actual PLC that's running our code. And we've dedicated one of its network cards towards being an EtherCAT master. So that'll go into what we have here was an EK1100. That's a bus coupler, and we had our digital inputs and outputs here. So essentially that's what we've got up to there, and then we just put an end cap on it and we're done after that. So we've got a very small system over here on our test bench, but this is an example of a much more complicated system. So you can have quite a bit of flexibility. So for instance, like this section could all be inside the control cabinet here, whereas this could maybe jump out of the control cabinet and go over to a conveyor, another conveyor, some extra motors, and then this could be out on the end of a robot, things like that. So what's really cool is that these sort of legs of the topology here, these are just RJ45 Ethernet, they can sort of just end wherever. You don't have to always hook them up, and everything will be happy. So on this one, you've got an input, an output, it goes over to another one, and then you can even put in extra slices, like if you wanted one here that had another Ethernet port on it, and it could go out somewhere else. So essentially this topology is incredibly flexible, and you can also set up ring topologies if you want, where you have some built-in failover for bad cables and such, redundant masters, all kinds of crazy stuff you can get into. So that's one of the things it supports that some of the other field buses really don't. Talking more about the other field buses, I think the best to compare it to would be things like DeviceNet and Ethernet IP. So Ethernet IP is Alan Bradley's sort of go-to field bus, and we can talk Ethernet IP as well through a Beckhoff PLC, but it takes an add-on license as well to actually talk to those devices. But Ethernet IP can talk to servo drives, it can talk to I/O, and it's got a pretty good hold on the market from what I can tell. But what I don't like about it is it actually runs on top of TCP IP. So what that looks like in the OSI model here, we've got, if you're familiar with the OSI model, that's some networking terminologies that aren't specific to industrial stuff. So you got the application, presentation, session, transport, network, data layer, physical layer. Physical layer is like the actual medium that the electrical signals travel on, all the way up through Ethernet MAC. Media access control is going to be like your MAC addressing and stuff like that, how it traverses through switches. That's your entire data link layer and buffering and such. Then typically the network is IPs, Internet Protocol, on a normal, like when you make a web request to go to google.com or some such, it goes all the way down this to the physical layer, bounces around the world, and comes all the way back up to the other side. So this is where Google server lives, all the way back down, all the way back up to your client. So that's what this OSI model is for. And essentially EtherCAT, you've got layer 7 here, which is where our PLC is actually talking to this, where you've got this mailbox, this magical mailbox access, and it skips all these layers here. And so those layers are typically software that run on a non-real-time system. So those software, or they can run on real-time systems as well, but in general, you get a lot of jitter and a lot of nastiness coming through this section of the process. So they just skip it here, and they jump right down to the data link layer. So what that gives them is a lot more real-timeness, real-time and determination. So, all right, well, let me bring up MS Paint here and just try to explain the difference between real-time and determinism. So if we wanted to, say, output a square wave out of our TwinCat PLC, and this is time across here, and that's our signals, 1 on top, 0 on the bottom. As we cruise along, we're outputting at some frequency. Real time to me depends on, whatever's listening to this signal, how quickly does it need to do it? So if you had one that, this would be a lower performance system and this would be a higher performance system, right? So if I've got to be able to do it this fast, maybe this is a nanosecond. All of a sudden we're in a real-time system there, but where is it that it becomes not a real-time system anymore? If this is a quarter second, is that a real-time system? So something like, a Python program on a Raspberry Pi that's toggling an output, you're sitting on top of a non-real-time system there typically. So a 1 millisecond cycle time might be reasonable, whereas with a PLC, something a lot smaller could be achieved, or at least on this real-time kernel that we have on TwinCat. And the same goes for things like Rockwell PLCs and such. So if you're getting down to that 1 millisecond kind of timing, that's real time, but of course the embedded guys would probably laugh at that and say that 1 millisecond cycle rate is not at all real time. You would want nanoseconds or something very, very much smaller. So real time really is context dependent, and real time in the industrial world is it may be 10 to 1 millisecond kind of range, somewhere around there. But in general, that depends on your application, of course. But what's more useful to talk about really is determinism. And so determinism is saying, regardless of how fast I go, let's see, I'll do a small one here. Regardless of how fast I go, is this, for instance, this rising edge, let's get it lined up. Is this rising edge that I'm drawing right here, is that going to happen at the same time? So is the delta between this rising edge and this rising edge going to be the same as the delta between this rising edge and the next one, right? So if those are near identical, then that's your determinism. And so the amount to which they're not identical would be the jitter in the system. So when we talk about EtherCAT, it's a field bus, but it's also a real-time deterministic field bus, which sets it apart from a lot of different stuff. So that's worth noting, because there are some other field buses that are real-time, but there's few, if any, that are real-time. Actually, I think there are a few, but there's very few of them that can perform real-time and deterministic. So one of those that's very close and used by one of the competitors and huge market shareholders, Allen Bradley, is Ethernet IP. So Ethernet IP has a lot in common with EtherCAT. Specifically, the topology is very flexible, whereas some of the other field buses are not. The thing that really has EtherCAT ahead, in my opinion, though, is it's just raw performance. It can do about 30 times faster of a frame update rate, and the determinism is pretty close, actually. But it's just absolutely deterministic on that network. So if it works, it's going to pretty much work forever and always. And I've actually seen that as well. It's been great. So moving on, one last thing to say about EtherCAT is that we actually use a system called device profiles within EtherCAT. So I'm going to pull this, just reading Wikipedia to you essentially here, but two of the main things is CAN open is something that a lot of drives use. You may see that on servo drives. Typically that's done over CAN bus. It sort of sits on top of CAN bus. And then the other one is Sercos interface, which is, I don't know what that stands for, servo drive profile, but this used to be connected with little optical cables. So it would run in similar fashion where you daisy chain the drives, and really high performance, deterministic, beautiful system, but very kind of expensive, very custom. So what they've done is encapsulated the Sercos over EtherCAT, and so, or servo drive profile over EtherCAT, maybe is what they call it. But essentially it's Sercos, and COE is CAN open over EtherCAT. So we'll talk a little bit more about these parameters and what they define, but think of it as, how do you actually get the data to and from these devices? So it's sort of ways of defining variables, like I want you at this speed. Well, the speed is going to be a CAN open or a Sercos kind of variable, if you want to call it that. So either a drive will run in one or the other. You wouldn't run in both, although a drive may support both profiles. So There's some pros and cons to each, but in general, the TwinCAT system, it abstracts all this, so you don't have to care, with just a few minor exceptions. So the last other thing is there is some safety stuff that you can do over EtherCAT. I haven't actually used it. I don't know how many people are using it, but that's the same with Ethernet IP. They have their own SIP safety system as well. So I don't want to talk about safety systems at all. I don't plan to, but that was the gist of it. I wanted to talk about EtherCAT, sort of what it can do and why we're using it, but that pretty much wraps this up. We can go ahead and bring in these drives over EtherCAT next, and catch the next video for that, and I'll see you over there.